Well, welcome everybody. Today we have Dr. Hannah Liu. Hannah is a tenure-track assistant professor at the University of Texas at Austin, with an appointment from the Department of Aerospace Engineering and Engineering Mechanics. She's also appointed as a core faculty member of the Odin Institute for Computational Engineering and Sciences. Before joining UT Austin, she obtained her PhD from Energy Science and Engineering at Stanford School of Sustainability, and then worked as a postdoc associate at MIT. Her research interests lie in the field of scientific computing, reducible modeling, uncertainty quantification, and machine learning in applications of environmental fluid mechanics. Well, Hannah, the floor is yours.
Thank you so much, Ruda. Thanks for having me here. So today I'm gonna talk about scientific machine learning enhanced forecasting in subsurface flows. So here I'm showing some pretty faces of my collaborators back to when I was a postdoc with my advisors Yusuf Mazouk, Ruben Juanes, and collaborator Luis Salo. And right now I'm in UT for a little bit less than 2 years. So I have my two students here. Some of today's work are done by them, and I have my collaborators here at UT, Hailun and Omar Gattas. All right, so let me move to the next slides. So I am mostly interested in subsurface fluids, where it plays a very important role in energy storage. We had a long history of studying subsurface flows, mostly before that's for oil and gas. But even for today, we're still heavily relying on fossil fuel energy. And nowadays, with a variety of new energy resources, it is very important to have a steady, sustainable energy system. And so we need renewable energy, but we need it to be combined with energy storage. And the subsurface is actually one of the resources that we can use to be the storage and use it to power our energy system. So this article here actually summarizes the challenges to be addressed in large-scale energy storage of different purposes. The subsurface operation is always related to geomechanical changes in like fault zones, and we're concerned about injection-induced seismicity. And for different energy storage, we consider different period of extracting them or store them for as long as we can. And they have also different properties, like for hydrogen, it's more reactive, it's more active to some microbial contaminant, things like that we need to consider. And subsurface is a very complicated system. If we just take CO2 storage for an example here, even without fluid mineral interactions, the process has multi-physics phenomena with multiple phases of oil and gas, CO2 and water. And in the fault zone, we need to consider multi-phase flow coupled with geomechanics to assess the risk of induced seismicity. And with different geological formations, there will be structural trapping and gravity-related trapping. And here we also see different driven forces. Near the wells, we have the injection pressure-driven flow, and in a much smaller scale, there might be buoyancy-driven flows and viscosity-driven flow. And here it also shows the very different scales of the system. The CO2 plume is in a very local scale, and the pressure migrate in a larger scale. But if you think about the stress and the strain changes, it is spreading even much larger scales. So also with the heterogeneity of the subsurface, this complexity of the process can be summarized into multi-physics, multi-scale, and full of uncertainties. So we do have physical knowledge about the system over many, many years from conservation of mass and momentum. We basically have these multiphase flow equations. Here, I'm only considering two-phase and not coupling with geomechanics yet, just for the simplicity. But from the two equations here, as you can see, one for saturation, the other for pressure, the coupling is through this flux of flux velocity, which is a function of pressure, and the capillary entry pressure, which is a function of saturation. And you can directly see that the pressure equation is parabolic, so it changes in a larger scale. And the saturation equation is hyperbolic, so it propagates in a smaller scale. And good thing about these equations are they are reliable in providing future predictions with their explanatory power and quantitative error estimate. But it is still very challenging today to simulate physics-based modeling because of its expensive computational cost. For example, this simulation for CO2 sequestration, it can take days to finish with this resolution. And as you can see later on in the simulation, some small scale, these beautiful dissolution fingers, it requires to be solved at very, very fine resolutions. So the simulation is expensive for one run. And because of the uncertainties, such as material properties of the porosity, the permeability, and the location of the fault, initial boundary conditions, and also the constitutive loss, which actually is hiding in this lambda here, contribute to a large set of uncertain parameters. If you represent all of the parameters in P here, then it is indeed a parametric system. So to assess different scenarios or design and optimization operation doing uncertainty quantification, you will need to run the expensive simulations many, many times at different parameter samples, and this becomes computationally impossible. So more recently, with the rise of data science, we have data-driven modeling as a tool of many application fields. And pure data-driven modeling, or we say classical machine learning, it comes from computer science in many applications, for example, image classification, where we have large amounts of data, but actually no physics or equations to describe them. The concept of prediction and error is more qualitative than quantitative. And the same with the recent popular large language models like our daily friend ChatGPT. So if we blindly through data-driven modeling as a black box for a physical problem, it may fit the data very well in training, but it may fail immediately at prediction. This is an example in my previous paper. Basically, the solid lines are reference and dashed lines are from a pure data-driven model, which has poor performance in prediction. So it will be dangerous to make big decisions based on these models for our environment, for our future planet, where some small errors can bring catastrophic consequences. So many challenges and attributes in this interdisciplinary field of using machine learning in complex physical problems. Part of my research is about how to use our domain knowledge to embed physics to respect these physical constraints in machine learning process and improve the predictive capabilities of data-driven modeling so that at the same time, we can take advantage of its computational benefits. And this part is more of general methodology development. And I had many works before regarding this methodology development, including some challenges of advection-dominated system, which you see the video before, how to preserve shock propagations, how to deal with parametric system, non-autonomous system, this kind of things. I also have some recent work of dealing with nonlinear manifolds or partially observed systems. But today I'm not gonna talk about this. If any of these topics are of your particular interest, I'm happy to talk offline about it. So the second part, which I want to talk more about it today, is how to learn the quantity of interest from sparse and indirect data, how to enhance the physics-based models by these sparse and indirect data, so that we can take advantage of the fast data-driven models and the reliable predictive capabilities of physics-based models. And the first part, I want to talk about how to learn physical quantity of interest. So let's just take a look at this particular example and think about why we want to learn quantity of interest. So this is a reservoir model which describes CO2 injection-induced seismicity, a simplified model, 2D one, where you see this pre-existing fault within this intersection of the cap rock and the storage aquifer. You have CO2 injection here. And again, as we mentioned before, this system has multi-scale phenomena. We see that saturation is in a very local scale, and the pressure buildup goes all the way in the injection reservoir, and the displacement is propagating in an even much larger scale. And the challenges here is this is a multiphase flow coupled with geomechanics system. It has a lot of coupling of nonlinearities. It also has large number of degrees of freedom, as you can see here in the zoomed in simulation grid along the fault zone. We need very, very fine meshes to describe the things in this particular fault zone, and we need adaptive meshes around its area. So it results in a large number of degrees of freedom. The second challenge is it also has high level of irreducible uncertainties. Traditionally, people quantify or describe the fault permeability, which is quite relevant to how you assess the induced seismicity risks. They measure the host rock around this fault zone and take some measurement data to estimate the fault permeability. But actually, the reality is the fault permeability is definitely more full of uncertainties, and we should use some stochastic models to describe it more accurately. And my collaborators from MIT, before has developed this stochastic model, which takes into account a lot of realistic considerations in terms of building a stochastic model to describe the fault permeabilities along this region. And as you can see here, it can have very complex distribution of the form that more than 2 moles behavior can happen, and it is also anisotropic in terms of the fault permeabilities. So we also have these high-level irreducible uncertainties to consider in this system. And if we think about the tasks, we are actually facing very demanding analysis tasks. The things we care about here is the fluids-induced seismicity in fault zone, and in particularly this zone. So if we think about as we do the injection pressure buildup and it brings up geomechanical changes reflected in this normal stress change and shear stress change. When the normal stress is very large and shear stress is very small, things are very stable there. But when the shear stress is small, when the shear stress is large and normal stress is small, slip will happen, and that might induce seismicity. So it is really this ratio of shear stress and normal stress, which we call slip tendency here, that serves as an indicator of fault instability. And when this slip tendency goes beyond a threshold, seismicity will be induced. So if we think about this problem, we come from these input sources of uncertainties, including the fault probabilities, which can have complicated distributions. And we have to go through these full field PDE systems, which typically goes to 10 to 6 or 10 to 9 degrees of freedom, depending on your grid mesh size. And it has to be very expensive simulations if you want to do it in a Monte Carlo simulation loop. And then you do the post-processing to get the quantity of interest you care about. And in this case, we particularly care about the risk indicator in this particular zone. And if you think about the dimension for your quantity of interest to do this risk analysis, it is actually a very, very low dimensional quantity to be assessed. And so here, our goal will be to construct a model from the data that's just in this particular region, so that we can directly learn the quantity of interest without going through the very expensive full field simulations. But if you think about how we derive the quantity of interest, we go through the full field simulation and we go to this post-processing map. And unfortunately, this post-processing map and the full field map evolution, they do not commute in general. So we cannot really have the mathematical model for this quantity of interest, in particularly for this fault region. And all we want is to construct a model for the quantity of itself alone. So we are motivated by this well-celebrated Morris-Wanzek formula, which is saying that, yes, indeed, it is possible to construct a model for this quantity of interest in this particular region alone. And it has this a very abstract form, which is describing as the evolution depending on a form like this, and also depending on some local kernel terms, and also depend on the initial of the full state, which often are treated as noise term here. But the problem is this is just an abstract formula, and in most of the cases in general, we do not have the explicit form of this flow map R and the kernel form K. And this kernel form K essentially is saying that the evolution of this quantity of interest, it does not only rely on the current state, but also rely on it from the very beginning of its evolution. And many of the times we can think about if we want to predict the weather for tomorrow, it probably is relevant the temperature, the weather of today or yesterday, and maybe finite days before. But we usually don't need to trace back to day one of the Earth. So we can use these finite memory assumptions, which essentially allow us to build an abstract form to this quantity of interest, which is saying that my quantity of interest prediction will be based on some finite history, past history of this quantity of interest itself. And also it will also depend on these sources of uncertainty here. And based on this formula, we can use this neural network to learn this unknown form of the model here. Essentially, what we need to do is we need to collect some past history of this quantity of interest so that future trajectory can be learned from the sparse data just within this particular regime without access to all the other regions that's not concerned here. And we can also add the parameter values here. And then we train the neural network from trajectories of different parameter samples so that we can learn the form of this model G. And after training, predictions for another parameter input which is not seen in the training data, can be conducted recursively at this new parameter P star here. So here we show the comparison of the previous example in the CO2 injection reservoir. We show the probability distributions obtained from the reference solution, which is using large number of expensive simulations in Monte Carlo, showing here in blue, and also the Monte Carlo of the same ensembles from this direct machine learning model, showing here in red. And we can see that although the distributions of the quantity of interest, the sleep tendency here, change significantly over time, and the direct machine learning model actually is capable of capturing the overall shape of the distribution change. And the difference between these two increase with time, as it is a time evolution model, so the errors accumulate over iterations. Here we plot the 10th percentile of the quantity of interest. This small number of training data set, which is showing here in blue dot curves, we can see it provides a very poor approximation to the statistics of the reference, which is showing here in black solid curves. Again, the reference is large number of Monte Carlo runs with simulations. However, with the same small data set, the training data set blue set, we combine with the direct machine learning model, which can reproduce a large number of accurate ensembles, and so we can approximate the statistics with a much better, higher accuracy, showing here in red. And here is the same for the 50s and the 90s quantiles. So the training of the neural network is actually a negligible fraction of generating the data, because the quantity of interest is of very small dimension and the size of the neural network is also small. So basically, the speed up for this UQ task is significant. And using the same computational budget to generate a small set of training data, and with a little bit extra effort in training the neural network, we can get a much higher accuracy in this quantiles estimation. Of course, we can also use this. We actually, in the paper, we also did some global sensitivity analysis using this direct machine learning model. Otherwise, it will require a huge computational budget to do this Monte Carlo for many, many times. And we can use this framework to applications for accelerated UQ, for policymaking, and for some remediation plans. And also within this framework, we are thinking about the input can be beyond the permeability, the fault permeability. It can also comes from the well location controls, the injection rate, and even from some other measurements. For example, more recent advanced technology of using INSAR data to measure the surface displacement could be also used to do the risk assessment for the induced seismicity. And in fact, my collaborators here at UT Austin, An Chen and Omar Gattas, they actually had some previous work in terms of single phase flow, using the INSAR data to infer some in a Bayesian inference framework to infer the uncertainties in the subsurface. And with these INSAR data to infer, we can get a better posterior estimation for the uncertainties in the subsurface. And with a refined posterior distribution to describe the uncertainties in the subsurface, we can then continue with this direct machine learning surrogate model to go to the risk indicators. Otherwise, without all of these detours, it will be very hard to directly interpret from the INSAR data to the risk indicators. So some of the continuing work along this line will be collaborating with my collaborators here to go through this line for multiphase flow coupled with geomechanics in terms of CO2 injection induces seismicity risks. Something more along this line, if we think about this framework, we have PDE for the full field states. And then we have this memory-based machine learning model for quantity of interest. And before we have this parameter input explicitly in our quantity of interest model, and we learned this parametric model. And in fact, if we do some mathematical manipulations, which is essentially with the assumption that if the post-processing map to get the quantity of interest is differentiable, then we can augment these states with the uncertainties and the parameters so that this system, the parameters can be part of the state as well. So if we regard the parameters as part of the system, it can also become the missing part. And it can give us this parameter hidden memory-based machine learning model for quantity of interest, which means that you can also neglect the parameters there and directly get this quantity of interest-driven learning. But of course, here the model G tilde will be different and can be different of the previous G, and the memory length needed for the model without the parameters can be different than the ones with the parameters. And so another example from a very classical quarter-5 spot in reservoir simulations is we have a random permeability field and we have a injection well in this corner and we have one production well in that corner. The traditional way would need full field simulation of the pressure field. But although the quantity of interest mostly to the oil industry would be just the production rate at this northeast corner. And of course, we can use the previous SAM direct machine learning model to replace the full field pressure simulations. But in fact, if we do this mitigation of parametric uncertainties, we can neglect the input of the parameters, which will be better to deal with in a practical setting because the parameters are indeed the uncertainties in the permeability field. That is something we are particularly uncertain about. So if we use this framework, what we can do is for different trajectories, we can collect chunks of input and output burst of data from the trajectories of the production rate as the training data. And we need no knowledge about the underlying permeabilities. And then during the testing phase, we only need a small time interval to start because we need this part of the history to start the evolution of this model. Then the model can do a pretty good job in the following predictions. And again, without the input of the uncertain permeability field. And these are our ongoing work, which is still showing some very preliminary result, but we already see some promising curve and very good accuracy. My student tested over 100 testing cases with very good accuracy there. So yeah, that is the first part I want to share about how to learn physical quantity of interest. And the second part, I would like to talk about how to integrate with experimental data, which we typically regard it as the ground truth. And speaking of CO2 storage, one of the reasons why we have a have a large delay of doing CO2 sequestration is that the ground truth of CO2 sequestration is generally unavailable. We know a lot of things about the CO2, geological CO2 storage. We know the physics of the migration and trapping, like the PDEs I showed you before. And we also know the storage capacity of geological formations in US and even around the world. We have a lot of knowledge about that. But in terms of the challenges and why we have this huge delay of large deployment, several things we mentioned before. One is geological uncertainties and the expensive simulations that makes the prediction, the quantitative forecast, to be very expensive. And the second thing is the ground truth is generally unavailable. We are talking about 30 to 50 years of CO2 injection, and we're talking about 100 years and even longer time of monitoring to keep the CO2 underground. So we don't have data of that timescales to validate all of our physics-based models against. So in this context, our collaborators at the University of Bergen put together what I think is a really fantastic experimental program. They have a name Fluid Flower. So what they do is all we care about here is to meet the knowledge gap to achieve reasonable timescales in the experiment. So they construct this lab scale size geological storage formation. And as you can see, it's a meter scale tank and quasi 2D with transparent glass panels. And they pour in different kinds of sands to mimic layers of reservoirs and seals and geological faults. And the CO2 is injected at designed location, and the plume migration is visible to track in these days-long experiments. They also added some sensors in the back of the tank to collect pressure data, and they have a series of experiments with different tank sizes, geometry, injection designs of the tank, and they're continuing the experiments in museums and in classrooms to educate the public and the kids. Here is the outreach they are doing, which has these very mini flowers for the kids. Very fantastic job. So this experiment has been used as the basis for a benchmark study, which are participated by 9 groups, simulation groups around the world. So basically, they asked the best subsurface simulators around the world, and they want to test if our best simulators can validate a real CO2 sequestration scenario, even it's just in a lab scale experiment. So they did it in a double-blind study way, which means the participating simulation team are not given the experimental data before they do the simulation. So the only data they have is some kind of material properties measured in this lab of the sand and the size, and they have this picture of what is the layers there. And most of them are choosing the same two-phase flow equations I showed you before. And they also used these Corey type constitutive laws. But there are some other things. Different teams have different choices. For example, there are many uncertain parameters in the system. It has to be estimated by the simulation teams independently, and especially the constitutive laws. It has to be tried for this crazy exponent here for one of the parameters, and you can imagine how sensitive it will be to the system. And for different simulation teams, they also have different numerical choices, such as the mesh size and the convergence threshold. And the don't allow the communication between the experimental team and the simulation teams, and also the simulation teams to simulation teams. So here is the fun part, the results of this double-blind study. So they compared the simulation prediction with the ground truth experiments, and this is for 24 hours. These yellow contours are the dissolved CO2, and the blue contours are gas CO2 from experiments. And the green shades are simulation dissolved CO2, and the red shades are simulation gas CO2. So ideally, you would want to see the green shades match with the yellow curve, and the red shades match with the blue curve. But you can obviously see the big gap between the ground truth experiment and with our best simulators in the world. And especially we realize that this vertical plume, because of the local fault there, has been very difficult to capture for many of the participating teams. And things just gets worse for 120 hours. One of the simulators just blow up and provides no result here. But again, one of the reasons of this big gap is because the experimental data is not given to the participating teams as a prior. And there are many parameters, especially for the constitutive laws in the system, are chosen by the participating simulation teams. So without model calibration, or they say history matching, we will have this big mismatch as expected. And things can be improved immediately after model calibration. This is the simulation results from my postdocs group at MIT. So it's some of their earlier work. After manual calibration with experimental data, you can see that the simulation model provides a very good representation of the experiments. And if you ask Louis, who is a main author of doing this work, he was in Bergen for many months just to do this. It has to be manually calibrated, and it's a very, very painful calibration process because there are so many parameters to be tuned in the system, and some selections can be made by his geophysical intuition, but in general, we don't know how sensitive the system responds to each parameter changes. And as we mentioned before, the simulation are very, very expensive, and we need very, very fine resolution to resolve these small-scale dissolution fingers. So to lift the pain in manual model calibration, when I joined the team during my postdoc, we want to use machine learning in this model calibration process. I'm just gonna briefly mention the surrogate modeling and the model calibration part today. So essentially, we want to learn a machine learning model, evolution model from the input samples in the parameter space to different output CO2 migration plume. And what we want to do next is to use the learned machine learning surrogate to conduct the quantitative sensitivity analysis and calibrate the model with experimental data. And the final product we had in mind, which we haven't finished, is to be a digital twin for this particular fluid flower experiments. This calibrated model will allow us to do transfer learning for different scenarios of geological formation and different injection plans. So I am super excited about this project as it can be a first step to enhance our confidence in a trustworthy prediction and real-time assessment for CO2 sequestration, even we're now just talking about lab scale. So in the machine learning model, we have 15 parameters in 3 different regions, and we encoded the structure of the fluid flower tank so that the input is actually 5 different images representing 15 parameters. And the other channel we have is the time. So we used image-to-image regression and used convolutional neural network, UNet, to do this task. And we predict for the output is a map of the CO2 dissolved in the brine. And so that we can make the best use of the spatial correlations. And we use a convolutional neural network structure to do this image-to-image regression. So here I'm just showing you a test case which are different from the training data. Here the first row is the true simulation data at different time snapshots. And the middle row we see is a prediction from machine learning. And the last row is a point-wise error map. And we want to point out that this is a very challenging task because, as you can see, a big part of this point-wise error actually attributes to the dissolution fingers from hydrodynamic instability. So the fingers don't necessarily have to be in the same place. And just to show you another test case where we have similar good results, but different plume features. And here we have the histogram of the Wasserstein distance between the test case simulation and the entire training set simulation at 4 representative times in these blue bars. It essentially shows the diversity of the data set and the complexity of the distribution, especially as we observe that these two modes behavior at longer time. So this evolution is kind of a similarity measure, reflects that our test case will not be a trivial interpolation from the training data. And this red vertical line is the Wasserstein distance between the test case simulation results and the test case machine learning predictions. So it is a better measure of accuracy than the point-wise error because the previous point-wise error mostly, as we said, comes from the dissolution fingers. And Wasserstein distance is a better metric for measuring the plume migration. So we see that the machine learning prediction accuracy remains less than 10 to negative 3, even when the diversity of the training data set spreads out at a later time. And we can imagine if we use some trivial interpolation like kriging or more trivial interpolation, we will probably do well at the beginning when the data patterns are quite similar to each other, but we definitely will do worse at a later time when this diverse pattern appears. But in contrast, our machine learning is able to maintain the accuracy because of the effective learning. And here is basically we are summing up the blue bars in previous slides in the bottom and the vertical lines in the top of this accuracy representation. And here we see that machine learning as a data-driven model, it will learn better from a more diverse data set. And it shows the fundamental difference between the machine learning and the conventional interpolation methods. And now we use the developed convolutional neural network-based surrogate model to compute the posterior distribution using MCMC. So showing here in this gray histogram. And here we use the manually history matched parameter values from our previous study when Lewis determined that, showing here in this red curve. And this blue curve shows our prior knowledge, which we assumed uniform distribution. And here we show 3 representative examples. For some of the example, for example, this one, the posterior is well constrained around the true value, which is indicating a strong identifiability. And in contrast, some other examples, the posterior are showing a strong update from the posterior. And the true values, for this one is closer to these tails and indicating bias and challenges in the inference. And given the ear-post nature of history matching or this parameter identification, multiple parameter combinations can match the observation data as well as, or even better than the reference solution, this red curve that's identified by my collaborator when he did it manually. So what we need here is a robust surrogate model to fully explore this possible space of all plausible solutions. So given this machine learned posterior, we also need to, many of these cases actually showing that we may need to revise the prior and assess inferred parameter combinations using domain knowledge. Like, for example, these strong skewness observed in this region may suggest that we need for a refined prior towards higher values. And some inferred combinations may also be physically implausible. So this means that we also need to further validations through either high-fidelity simulations or experimental data to guide and constrain the parameter identification process. But nevertheless, this current machine learning surrogate was trained with not a limited data set, not big enough to cover all of the possible scenarios in the parameter space we would like to consider. We also need to improve the generalizability, and there are some other things like graph neural network that we want to consider, but I think I probably want to skip that slides because of the time. In general, with that conclusion is we make some more effective use of the experimental data in terms of improving the prediction capability of our existing models. And it appears to be a very useful tool towards building digital twins for at least these lab scale experiments. And I'm going to skip many of the other slides and going to the last one. So as we said that the quantitative forecasts are very challenging because of the geological uncertainties and the very expensive reservoir simulations. And one thing I have been working on is to learning the quantity of interest directly. And the second thing is the challenge is coming from the ground truth is generally unavailable. So the efforts has been done through the experimental side that doing lab scale experiments and trying to calibrate with the existing physics-based models. But of course, if we go beyond the lab scale, if we go into the real world reservoir scale, basin scale simulation, basin scale, like real world, there are still so many challenges because unlike in lab scale, we don't have that luxury full field data. All we have is more sparse and indirect and noisy measurement data. And we still have a lot of challenges to deal with the real world reservoir scale and the basin scale things. But I think the only hope will be combining all of the efforts from the experimental side and our existing knowledge about the physics-based simulations and the arising machine learning tools all together to addressing this part of the challenge in the real world scale. I will stop here and try to answer some questions.
Thanks, Hannah. Any questions from the audience? Please unmute yourself.
I have one quick question. First of all, thank you for the talk, very interesting. Like you, in the beginning of the talk, you insisted that we have to do physics somehow for this kind of models. But then towards the end, I was just wondering, like, are you embedding any physics in the way you train your machine learning? Because that looks like, I think you are using like a unit, so there is no, you are like image to image regression. So the physics does not add anything in terms of accuracy, or it's just like clarification. Do you have like a physics terminate, or you don't need it for this particular application?
Yes, for this one, we actually have the physics in the sense that we're training from the simulation data, which are based on the PDE-based simulations. And we use that to identify the parameters in our PDEs. And essentially, the surrogate model is a good representation of all the simulations. And going way back, we are still trying to figure out the best parameters in the PDE models that can best represent the experiments. And that is how we still rely on the physics. Although from the simulation data training to a surrogate model, here it is a pure data-driven machine learning model. But of course, something we also had in mind to enhance the robustness and the generalizability is one thing could be adding some physics-informed penalties in the loss function from the simulation data-driven modeling in the machine learning part. That is also something we had in mind to do in the future.
Perfect. Thank you.
Thanks.
Yeah, all right. So it's an excellent talk. So can you go to the unit slide? I need to understand that whether you are not using the dissolved CO2 map in prior time step as an input. The input is only the parameter of the system and the snap, right?
Yes.
Then you are training for every dissolved CO2 map, the whole thing, and so that like next time you give for next time step, it can predict the dissolved CO2 map. Okay, I see. Yeah, but I'm wondering this type of models are specific for some particular domain. Generalizing to any arbitrary domain could be additional work. Um,
Yes,
yes.
this is a very good point. As you captured here, we encode the time here in the input channel, which I have to admit it will not be the best way to use the data. Um, so so we are also trying to use it as an evolution model, which means here actually you can get the input of the current time step of the dissolved CO2 map to predict for the next time step. That could be a better use of using the time relevance between current time and the next time step. But also, again, because the current data set is also setting in a fixed simulation window, that is also part of the reason why the current framework works. But I do agree with you, the time evolution model could be a better use of the correlations in the temporal scale.
Yeah, so no, my another point was like the domain, the rectangular domain you used. If you change the domain, you have to update the model.
Yes.
That's also another thing that you need to consider. And in the Morris-Wanzai formalism, did you, I mean, like, how do you choose the number of steps or the prior data you are going to take?
That is also an excellent question. In general, I would say it's problem dependent. That is, so essentially the Morris-Wanzai formula gave us a motivation of the model might look like this. First, it doesn't tell us what is exactly this G, which we deal with is learning from neural network. And it does not give us the answer, how long is this memory, which in practice, we try this number to see what will be the best number. And in practice, I would say that when you are using too short of the memory, of course, it will affect the accuracy. But when you're using too long of the memory, one thing is you definitely need a longer initial data. And the second thing is, in terms of neural network training, it's also not a good idea because many of the smaller weight will become kind of noisy, and it will not be. So there will be some sweet spot you can try practically to get the best memory length there, and that's also what we tried. But like for the example here, I think most of my simulations goes to 20 days, but it's like 200 time steps. And the memory length I used is 10 or 20, that kind of order. And then after that, it's doing the evolution.
Right. Thank you so much.
I have
Thanks.
like a very quick follow-up question on that. Can you go back to your equation where you are showing that? Like the one back once more.
Yes.
The one where you have this recursive, yeah. So when you do something like this, do you basically have some sort of a error propagation over time, and like you would need to have to kill, like you know, there are a couple of recent papers where people do something like this, but then at some point they realize that your model starts to somehow diverge from the physics. So once in a while they're calling like a physical model to somehow get back on track. Is that something that you plan to do, or that's something that is irrelevant to your case?
So in my case, the one thing is the physics model actually holds at finite time, because the simulation we run is you do this injection and the pressure build up, and we will see the slip tendency going bigger, and it will hit some threshold. So what we do is when it hits the threshold, we have to stop the simulation, because it actually means the physics might change at that point. And even the PD model we have here, multiphase flow coupled geomechanics, will not hold anymore. And your machine learning model is training from that physics-based model, you wouldn't expect that will give you any further predictions if their learning a model has limited horizon to be valid. So what we want to do is when it hits that threshold, we stop everything and we think there is a risk there and we need to consider. But when physics change, of course, everything change.
Thank you.
All right. I think that's all the time we have. Thanks, Hannah, again.